Kia ora tātou. Okay, rolling up my sleeves here. Material science and engineering, what is it? What have I been doing? And what happens if I push this? Or other things. Okay, so material science and engineering, what is it? So a great subject for the inquisitive. Essentially helps to understand the things around us, generally the solids. Generally we're trying to relate how they behave, their properties, to their structure. And once we understand that and how we can process differently to influence structure, then we can have some control. Okay, so that's what I like. Okay, the significance. So I'm hoping that these eras can convince you of the importance of materials. You know, eras have had their names defined by what might have been the leading materials that were being used at that time. And so, you know, showing the underpinning of technological development. More perhaps basically than that, materials are what we use to support our daily activities and achievements. So what's our choices? Okay, so in terms of material options, generally the area of materials divides the whole spectrum of materials that exist into four main generic materials groups. Metals, ceramics that get lumped with glasses, plastics and composites. And composites, that's a bit of a cheat because they're made up of materials from the other groups. Okay, so in terms of what we've got to choose from, that's it. So I raised this in terms of if we decide we don't want to use materials from a particular group, say often plastics can get a bit of a bad rap, then it means that we're either choosing from another class of materials that might be heavier and pay some penalty in another way, or we're thinking we'll do without it at all. Okay, so the other thing that I've raised on this slide is the impact of what material we might choose in terms of the design that you might end up with. So there's different ways of solving the same function with different materials. And it depends on the precise nature of what you want, you know, what sort of performance you're wanting from that design. Okay, so that's good stuff about materials. The negative, so the elephant in the room, a really big elephant in the room. But it's not the materials, it's themselves, it's how they're being allowed to kind of flow through society that's causing the problem that we need to address. So how do we address that? So we can take inspiration from the circular economy. So this is an alternative concept that's been put forward as an alternative to the current, what we consider to be the extract, produce, use, dispose flow model. And so it would take a long time to cover this too deeply. Probably a lot of you have seen this before, but in terms of the main things to take from this for now are the fact that if we want to have circularity and to avoid materials being released into the environment or ending up in landfill, we've got to think about how to circulate them back into further use. And the main alternatives are biological or regenerative cycles and technical cycles. And that's what the materials that my group have been working on are focused on, supporting the use of, supporting those cycles occurring. Okay, so renewable materials and recyclable materials. Now, in terms of renewable materials, this graph is kind of a useful inspiration for me in terms of where should we be looking, what sort of materials could be useful, and here we're talking about structural applications. So on the axes of that graph, we've got things important in structures, strength per dollar, and on the bottom axis, stiffness per dollar. And in an ideal world, we'd be in the top right corner there. Now, I've spent a lot of time with natural fibres, and I think this can justify the fact that here we're seeing that kind of purple bubble with the green bubbles within it. That's a collection of natural fibres that we can choose from, and they compare very well with the materials down at the bottom. There's carbon steel down there. We've got concrete down there, and so that gives us a inspiration to know we might be looking in the right place with natural fibres. They are renewable and potentially high-performing materials. However, generally we've got to incorporate them within a housing material, what we call a matrix, to actually make a continuous material that we can build stuff with. And so that's what I've spent a fair amount of time doing. That's a big challenge because the materials, the fibres, are generally not very compatible with the materials that you're wanting to combine them in with. So to get high performance, there's the challenge. And my group has looked at across the kind of continuum of looking at how to extract the fibres from the plant, to how to modify that, so surface treatments, that sort of thing, as well as how to incorporate them and the manufacturing processes for producing composite materials, alongside the improving design with them. And so there's a little example. I don't know if I've got a pointer here. This bottom here, I'm moving, aren't I, from the spot? Oops. So that design there, that represents designing with minimal material to produce a structural panel that could be used in a housing situation. But some other structural products there for the sorts of things we're looking towards. This is at the side of, so that there's our renewable materials that we're looking at, but also we're alongside that we've got research going on recycled or waste materials, such as recycled plastic, paper, cardboard, and wastes such as building waste, such as treated timber, so chrome, copper, arsenic treated timber, mussel shells, collagen from sheepskin that currently go into landfill. Back to natural fibres. So this is one of the fibres we've been working on, hemp fibre. We see that when we talk about hemp fibre, in actual fact, there's more than one type of fibre in the hemp stalk. Mainly, there's bast on the outside, the strongest, stiffest fibre, and on the inside, you've got hurd material. Now, they look different when you look closer up at them, and structure informs properties. They behave differently too. So the bast in the centre, much more lower performing than the bast material. We can take these lower performing fibres, follow the track along the top, and we can take that material, process it, and say make 100% bio-based particle boards that we could use for in your housing applications, and formaldehyde free, and more importantly, you could recycle that material at end of life. And on the bottom layer, we're showing the use of higher performance fibres, and from those we can make composite materials that we could extrude, such as for 3D printing filament as being shown produced there. So then we can print whatever we like from that, or we could also do other manufacturing operations, including moulding with that material. Breathe. Okay. So how well are we doing with our higher performance materials? Well, this is an example based on 3D printing filament that we've produced. We've produced over 40 different types of 3D printing filament now, and hopefully you can see there tensile strength and Young's modulus relating to stiffness, so strength and stiffness on those axes. And in terms of comparing our materials with those in the literature and commercially available, our green circles there, we're performing pretty well compared to other ones. So we're very proud of having spent the time understanding the nitty-gritty, the whys, and putting that into action. What else have we been doing with it? Well, in terms of, we've actually got some commercialised filament now, so that's our first cab off the rank there. That polywool product, but we can do, as I mentioned with 3D printing filament, we can do whatever we like with it. So there's an example of a commemoration trophy that we've printed based on a little figure from something that meant something to the family of the person who was sadly departed. Further than the 3D printing, we've had an interest in 4D printing. And so 4D printing, for those that haven't come across it before, it's you 3D print something, and then the fourth dimension relates to a response over time to some stimulus, which could be here, moisture. So here we see components that we've printed in flat strips, And the way we've printed it and the materials that we've used to print it from, we can engineer that such that we can get it to fold or twist. And one little example demonstrator shown here is a suggestion of shutter material that you could put at a window, and on a dark, damp day, when it's moist, that will open up just like that pine cone kind of effect. And then when it's bright and sunny, it will close to allow better room comfort. We can also get heat response. So this is shape memory, so you can scrunch that up and then heat it up again, and it will return to the same shape as we've just seen it get to. Okay, so all with renewable materials. Something that's extended beyond just the materials domain since 2000, but has also helped accelerate the progress made with these materials is a project that I led, Omio Mio Aotearoa, a circular economy for the well-being of New Zealand. And so that was essentially taking account of the social science aspects, and so understanding what would help people adopt these materials, what would actually get them more accepted, and taking account of getting the best benefit for people as well. It's all about people. Kind of linked to that, and excuse the book plug, but but unless people read it, it's not going to make a difference, and that's why we're doing this work. So that's coming out soon, Circular Materials and their Implementation for a Sustainable Future. Okay, and how I feel, I've seen a lot of acknowledgement slides. I think it takes a village to raise a Royal Society Fellow. So there's so many people to say thank you to, and some of them are represented here. Of course, to the Royal Society for their recognition, and particularly to my family. So Tim, my ongoing supporter, and my kids there, Rebecca and Isabel, and also to my many collaborators. And before I get thrown off the stage, I just want to have one final slide with a quote from a doctor who is more famous than I will ever be, Dr. Zeus. And this is what keeps me moving. Unless someone like you cares a whole awful lot, nothing is going to get better. It's not. Thank you.